So what is the Big Bang Theory? It was not an explosion as the name would suggest, but rather the creation of all the universe in space. And it started as a small, dense core and then started expanding outwards, creating the universe as we know it, which is still expanding to this day. Now, there are three main pieces of evidence to support this claim, the first being redshift. Now this is the change in frequency of waves, like light waves or sound waves, as they get farther away from the observer. Now the way this relates to the Big Bang Theory is we can observe the light coming from far galaxies and see that the frequency of waves is actually getting longer, and we can tell that they're moving away from us. The second piece is cosmic microwave background or cosmic background radiation, which is the light and energy left over from the original Big Bang. Now scientists can observe this energy and speculate about what the early universe was like. Now, the third piece of evidence is the fact that there's all matter in the universe. We can tell that it was created from the Big Bang. All the matter that's in stars and planets and all of us. And we can use this evidence that the Big Bang actually happened. Let's talk about matter. Matter is any physical thing that takes up space and has mass. For example, a banana is considered matter because it takes up space and therefore has mass. Sound waves, like the ones that I'm conveying to you, are not matter because it's a movement of air molecules not actually taking up space, so therefore it has no mass and is not matter. Alright, now let's move on to stars. Stars produce elements by combining two elements it already has through a process called stellar nucleosynthesis, which is creating new elements through the process of fusion. Like, for example, a main sequence star like our Sun creates helium using two hydrogen atoms. Now, higher mass stars can create elements like iron through fusion neon. And when it becomes supernova, it can make some of the heaviest elements on the table. Now, the way we figure this out is by observing the electromagnetic spectra given off by the stars, which is the pattern of colors in the star's light, which change depending on the elements being produced. Now, do not confuse nuclear fusion with nuclear fission, because they're two completely different things. Fusion is the combining of elements, but fission is when an atom loses protons and then turns into a new element. So, energy from the sun begins in the core, where nuclear fusion is taking place. The energy is then transferred to the next layer, the radiative zone, in the form of light particles, which then escape to the convection zone. A convection is the process in which heat rises and cooler sinks down. It is in this zone where light is created. The light then travels through the photosphere, the chromosphere, and the corona, where solar weather takes place, like solar flares and such, and then it travels through space to reach Earth in the form of solar radiation. So this is an example of a Bohr diagram. Now this illustrates what an atom looks like and what each element looks like. Now this in the center is called the nucleus. It contains all the protons and the neutrons in the atom. I've chosen oxygen as my example, which has 8 protons and 8 neutrons and 8 electrons, which are stored in these outer shells. Now this first shell is filled up because the first period is just hydrogen helium, which in the first period only has 2 protons, 2 neutrons, 2 electrons. So that first shell is filled up. The second shell comes when you move on to period 2. Now this is where it gets interesting. Because the second shell in period 2, it's only gone up to right here, where it only has 6 outer electrons. Now the electrons in this outer shell are called the valence electrons during the outermost shell. So you can kind of tell where it is in the periodic table, kind of what's going on with it based on how many valence electrons it has. Now, the electronegativity means how much each atom wants to gain more electrons, because each atom wants to have full shells, which means it either wants to lose a bunch of extra electrons or gain some more to fill up the shell it has. Now, oxygen is pretty high electronegativity because it only needs 2 more to fill up its current shell. Now, an element like let's say lithium with 1 valence electron wants to get rid of that last electron so that it can have a full shell. So that means it has low electronegativity. So the periodic table is sorted into many different sections. This section over here mostly being nonmetals with 1 metalloid. But the way we know that chlorine is a halogen is because this section right here, along with fluorine, is the halogen section. And then these 3 over here, lithium, sodium, and potassium, are all alkali metals. And it is specifically said in that section. Remember over here is alkaline metals. Alright, let's take the elements sodium and chlorine, which when combined form an ionic bond, which is when electrons are taken but not shared. Now, these 2 create salt, and they create a pretty stable equilibrium because, as you can see, sodium has 1 extra electron in that outer shell, and then chlorine has 1 extra spot in its shell that it wants to fill up. So when sodium gives that electron over to chlorine, they both have full shells and they're both happy. So one final thing. We know that Na and Cl combine to make 1 very stable combination. But when they're alone and they're very, very close to a full shell, they're very, very reactive because they really want to get rid of that last electron or gain that last electron. So they're really dangerous and unstable alone, but when together, they make 1 very safe thing.